Mm-hmm.
First of all, this one right here. Oh, hold on. Sorry. Just a second. I may have led you astray when I drew a bunch of scalene quadrilaterals and they all looked like they formed equilateral quadrilaterals.
Mm-hmm.
And I kept telling myself, well, this is really amazing if it's true. That you could have a scalene quadrilateral, connect the midpoints, and that's an equilateral. It just couldn't seem like it was true. But I couldn't disprove it. And then I looked at F, the rhombus, and I realized that you could draw a rhombus like this. And clearly, that distance is not, it's smaller than that distance, right?
Mm-hmm.
And so the fact is that I can draw a rhombus whose midpoints do not create a equilateral quadrilateral. Well, what happens as this angle 1 becomes bigger? Well, that still does not. That distance is still the shortest distance.
Mm-hmm.
And it's only when it becomes a square where the midpoints are going to be equilateral.
Mm-hmm.
And so what is the answer to F?
Answer to F is
It's never. In other words, the only way that you can create a rhombus with the midpoints being an equilateral is if it's a square, and then it is also equiangular. So it's only when the rhombus becomes a square that you get both. And at no other point in time is it ever equilateral. So there is no point where it's equilateral and not equiangular.
mm-hmm.
And what that caused me to realize was that if you have a scalene quadrilateral, then joining the midpoints is never going to be equilateral, ever.
Mm-hmm.
Now, proving that is a little tougher, but I realize there's one way you can probably prove it. That is, if you create a trapezoid, no, actually, let's create it like this. There is a scalene quadrilateral. No two sides are the same. And then what you do is you label that x sub 1, y sub 1, you label that x sub 2, y sub 2, so forth and so on. And then you can actually use the distance formula to prove that these are never equal to one another.
Mm-hmm.
So that is the thoughts I had about those two problems. Did he give you the answers to those two?
Yes.
What were they?
I think you're right. I don't remember though.
Okay. These are very, very, that's graduate level geometry if you want to know the truth. to prove that a scalene quadrilateral will never produce a scalene equilateral from its midpoints.
Mm-hmm.
I mean, that is it truly is a graduate college level proof. I don't have any problem with your teacher giving you those kind of problems because it causes you to think a little bit more in depth about geometry than you normally would.
Mm-hmm.
So, for today, do we have any new stuff? Yeah, I see we do.
Yeah.
Let me open up the first one. Can almost open it up. Yeah, that's as far as I can open it up right there. I guess that's fine. Do you have this in front of you so you can read it?
Yeah. It's just a packet because we had a snow day yesterday.
Yeah.
It's more like busy work than actual.
Okay.
Stuff.
Well, I can't blow this up any bigger, but I think I can read it as long as you can read it.
Yeah, I can read it off the thing if you need help.
Yeah, if you can't read it off of my monitor, then read it off of your paper.
Okay.
All right. Refer to the diagram and complete. Triangle CAR, which is this triangle,
The smaller.
is that must be congruent? Is that the congruent?
It's similar.
That's the similar sign. Okay. Of course.
Yeah.
Of course, yeah. To which triangle?
KSA.
Yeah. How come they're similar?
Because it's just a dilation.
Well, you can actually prove that they have three similar angles. In other words, that's the same angle in both triangles, A.
Mm-hmm.
And you can prove that because these two lines are parallel, well, then that's the same as that. And that is the same as that. So whenever you have angle, 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 then you have similarity.
Mm-hmm.
And angle S is equal to which angle?
Angle R.
Okay, yeah. Or ARC.
Mm-hmm.
Okay. Yeah, it's actually incorrect to call that angle R. It's correct to call that angle S. That is correct. But this angle R is not specific enough. The only way to really define that angle is ARC or CRA.
Mm-hmm.
Even though when you say angle R, I know what you're talking about. In reality, angle R is that angle right there. It's 180 degrees. Okay, let's look at the next one. Tell whether the triangles are similar or not.
They have to be similar because of the two angles.
Yeah, if you have two angles the same, then you have the third one the same.
Mm-hmm.
So yes, for that one. This is 55. What are these measurements here?
55 and 40 on the first triangle.
Okay.
And then 55 and 86 on the next triangle.
Which makes this other angle what?
39.
Are they similar?
No.
Okay. As long as you have one angle that's different, well, I shouldn't say that because sometimes these are not oriented the same way.
Mm-hmm.
In other words, you can have, similarity, if I draw a triangle like this, and this is 39 degrees, and I draw another triangle like this, and say that this is 51 degrees, and that's a right angle, and that's a right angle, are those similar?
No.
Actually, they are.
Yes, they are.
They are, because this has to be 51, and this has to be 39. So you do have angle, angle, angle. It's just they didn't present it to you as angle, angle, angle. In other words, the only way to prove it, that it's similar, is you have to figure out all three angles.
Mm-hmm.
All right, number 7. Are those similar?
Yes, they are, because of the
They
vertical.
Yeah, and whenever you see that kind of a diagram, they're always similar. Main reason is those are vertical angles right there. You got a 90-degree angle there and there. So this one has to be the same as that one.
Mm-hmm.
All right, on number 8. Are those?
They are.
Sorry, I didn't hear.
Yes, they are.
Yeah, because that's the same on both triangles. And we have one angle that's the same, which means this has to be the same as that also. Even though they did not tell us they were parallel lines. Notice that they didn't say that these two lines were parallel. Had they said they were parallel, then we would know they were similar also. But instead of telling us they were parallel, they told us that that angle is the same as that angle, which also tells you they are parallel.
Mm-hmm.
Those two angles can't be equal unless those two lines are parallel. All right, number 9. Trying to look closer. This looks like 70.
Yeah, 70 and then 38.
Okay, so that's got to be 70 because I see those hash marks.
So that would be 140, and then the top would be 40, so they're not similar.
Yeah. Big fat no. Okay, number 10.
Yes. They are.
Yeah, there's 2 reasons they're similar triangles. The biggest is that you're looking at a parallelogram, correct?
Mm-hmm.
I think it has to be a parallelogram if you have 2 opposite parallel sides. And all parallelograms, when you draw a diagonal, you create 2 similar triangles. If you had to prove it with a 2-column proof, then you could say that that angle has to be equal to that angle because of the parallel lines. And then if you rotate it 90 degrees, let me think for a second. You also can prove that this angle is equal to that angle. So we have angle, angle. And that's really all you need to prove similarity is angle, angle. Well, yeah, no, that has to be true. Because if you have 2 angles that are congruent, then you have angle, angle, angle. Have to. If you're dealing with triangles. So you really only have to prove 2 angles.
Yeah.
All right, number 11. Similar triangles are shown. Find the values of x and y. Let me redraw this figure just to make it a little bigger and make sure I'm labeling it properly.
Mm-hmm.
Let's see. This is 6, 8. This is x. This is y. This is 12.
And then the bottom is 26.
26?
Yes.
Okay.
So
Give me a
we could,
ratio. This is
yeah.
basically a ratio problem because all similar triangles are ratio problems. In other words, if I have a triangle there and I have a similar triangle over here, and that side is x and that side is 2x, well then if that side's y, that's 2y. And if that side is z, that's 2z. In other words, similarity implies that the ratio of corresponding sides are always the same. Okay? So, how do I figure out this? Give me some ratio equations that I can write.
8 over 20 is equal to x over 26.
Okay, so that solves for x. So x is 26 times 8 over 20. Notice that it's not useful to cross multiply here. You only need to multiply both sides by 26. And then that reduces to what? Let's see. 13, 10, 4, 5. So we get 40 or 52 over 5 is what x is equal to. And then y. Give me a ratio for y.
Um,
I don't think it depends on x, does it? I haven't looked at it close. No, I don't think so.
No.
What's the ratio? Do it as simple as possible.
6 over y is equal to 8 over 12.
That is as simple as possible. As opposed to 8 over 20 is equal to 6 over y plus 6. This is far simpler. Now, in this case, the variable is in the denominator, so you do need to cross multiply.
So you would get 9.
Correct. All right, number 13, challenge. Okay, here, I'm going to redraw this. I've seen this problem many times. It's a classic problem. You'll probably see it on the SAT. What's this left hypotenuse? 15?
Yes, 15.
And this is 12. This is
And then
9. This is x, and this is y?
Yes.
Okay. And I want you to solve for x and y. And the other important piece of information is that is a right angle. So, give me one equation. In other words, when you see a geometry problem like this, the challenge is to come up with equations. It really is. Just come up with one and see if you can solve it.
9 over 15 is equal to...
These two triangles are not similar, nor are they congruent. First of all, I want you to see that there are two different triangles. There's this triangle. Give me an equation for that triangle. That's a right angle. Pythagorean theorem. Give me the Pythagorean theorem for that triangle.
A squared plus B squared equals C squared.
Which translates to what?
9x squared.
9 plus x.
9.
And that's the hypotenuse. Let's start with the sides. It's okay to start with the hypotenuse. Okay, now I'll give you that. 9 plus x squared equals what?
9 plus x squared equals 81 plus x squared.
No. Pythagorean theorem says the hypotenuse squared equals the sum of the sides squared. Well, one side is 15 squared. The other side is y
squared.
Okay, so there's one equation. Has two variables in it. We cannot solve it. Now let's look at this triangle. Give me an equation for that triangle.
X squared plus 12 squared equals y squared.
Now at this point, you should realize that you can solve this. You have two equations and two variables. That's all you need. Okay? It's not necessarily trivial to solve, but let's give it a shot. Here, over here on the left, I'm going to solve this. Let me think if there's an easy way to solve it. Actually, there kind of is. Well, let's go ahead and expand the top one. So we get 81 plus 18x plus x squared, right? Equals 225 plus y squared. Now, y squared is equal to x squared plus 144, right? So let's substitute that for this y squared up here. So now we're going to have 81 plus 18x plus x squared equals 225 plus x squared plus 144. Now we have one equation and only one unknown. And notice the x squareds even cancel out, making it really easy. So now we have 18x plus 81 equals 369. Move the 81 over. We have 288. Divide that by 18. And we're going to have 116. So once you solve for x, now it becomes really easy to solve for y. Use either of these two equations over here to solve for y.
Okay.
In other words, y squared equals 16 squared plus 144. 16 squared is what? I don't know. You got the calculator. But you can solve for y. And you are going to get a plus and minus value for y, but whenever you're dealing in geometry, you throw out your negative values. You cannot have negative dimensions of a triangle. So if you come up with two solutions for y, which you will, because when you take the square root of both sides, you're going to have a plus and a minus. You throw out the minus.
Okay. I got 20.
20? That sounds right. I'm sure that they would come up with a whole number. Oh, it's 2 squared, or 16 squared must be 256. And then that's 400, and therefore y is plus or minus 20. Yeah. Okay. All right. Let's look at the next page. Ah, thought I had it. I wonder if I can do it this way. Well, that is weird. That's got to be a bug, isn't it?
Yeah.
In Windows. But that's okay. I got it to a point here where I can read it now.
Yeah.
Okay.
So, in the first one.
So, tell whether polygons are always, sometimes, or never similar.
So 2 triangles are sometimes, because you can have 2 similar triangles, but they're not always similar.
Hold on one second. Let me get so I can write here. Yeah, 2 triangles are obviously never always similar. And so sometimes they are. That's a pretty easy one. 2 congruent pentagons.
Well, if they're congruent, they have to be similar, so I think that's always.
Yeah, congruent would mean they have 5 same angles and 5 same sides, just like congruent triangles. When you have 2 triangles congruent, they have to have the 3 same sides and the 3 same angles. So that same congruent word applies to pentagons, and so always. If something's congruent, it's always similar. It doesn't matter what it is. If something's similar, it isn't always congruent. In other words, congruency implies similarity, but not vice versa. 2 regular octagons.
That's always true, because they're all the same length.
Yeah, they can be different sizes, but they're always similar. A rectangle and a square.
That's sometimes, because can't rectangle be, or a square is a rectangle?
There's a rectangle, there's a square. Those are not similar, but guess what? That's also a rectangle. So if I draw a rectangle and another rectangle that's exactly the same, they are similar. Or I could just draw 2 squares that are different sizes and they're similar. And one is a rectangle and one is a square. This all comes down to the definition of rectangle. In other words, squares are rectangles also. A right triangle and an isosceles triangle.
Well, I know it's not always.
Right, because you could have an isosceles triangle like that, and you could have a right triangle like that. Well, I drew this as I meant to draw it like that. So it's not always. Are they ever?
Yeah, if you draw a right triangle, and then the other 2 angles are 45 degrees.
Yeah. In other words, if I draw my isosceles triangle like that, so that's 45, 45. In other words, if the vertical angle is 90, well, then that's the same as this, where that's 90 and that's 45 and 45. Because all I've done is rotated one relative to the other. But they're still similar. So sometimes. Parallelogram and a trapezoid.
I think that's never, because a trapezoid doesn't have 2 sets of parallel sides.
Correct. I believe. I'm not 100% sure, but I'm pretty sure that the definition of a trapezoid is you only have one set of parallel lines. The other two lines cannot be parallel. That is not a trapezoid. You know, I'm 99% sure of that, but I'm not 100% sure. You kind of got to look up the definition of a trapezoid. Most definitions of trapezoids that I've seen say that it's one set of parallel lines only. The other two lines cannot be parallel. Okay. So number 7, referring to these two figures, what is the scale factor of the first one relative to the second one?
Well, if we just do 25 over 45, then we get 5 over 9.
Does your teacher like to have the small relative to the large, or does he like the large relative to the small? And I just answered my own question. He says A, B, C, D relative to A prime, D prime. So that would be what again? It definitely is 25 over 45, 5 over 9.
Yes.
Personally, I always like big to small. And the reason is I would rather deal with numbers that are greater than 1 than less than 1. Whenever you do small to big, you're always going to be dealing with fractions which are less than 1. And I have found that most problems, it's much easier dealing with fractions that are greater than 1 when you're dealing with similarity of polygons. So, first of all, okay, I guess by definition, AB is the similar or the corresponding side to that AB, huh? Because they could have been rotated. In other words, they're not rotated in this diagram. So you can tell that that bottom side is the corresponding side to the bottom side of the other one. You won't always be able to, but you will always be able to use the letters. In other words, if they're going to call this A, B, C, D, and this one A prime, B prime, C prime, D prime, then you can always assume that AB is the corresponding side to A prime, B prime. Okay. So angle C is what? Or angle C prime?
It's 82 because all the angles are equal.
Yeah, you can pretty much just go through. That's the only angles we have. So that's the only one we know. Find B prime, C prime. Now, here's a situation where big to little works better than little to big, right? Because I know that this distance is 9/5 times 30. Right? It's bigger to little. So it's one expression only. If I'm going little to big, then it's 5/9 of some number equals 30. And that number would be 30 times 9/5. It's a much harder problem. So this is a perfect example of why I like big to little, not little to big. Okay. So 9/5 of 30 is 54. So that's 54. Find DC in terms of K. Or D prime, C prime in terms of K. So what is it?
It would be 36K over 5.
Give me the basic equation. It's 4K. times 9 over 5, right?
Yeah.
Yeah, that tells me you understand it. When you give me 36k over 5, I haven't done the math yet. So, in other words, I always like starting at the beginning. And yeah, you actually cannot simplify that. It is 36k over 5 as a final answer. Again, big to little work better. What's the ratio of the perimeters?
Just 5 over 9.
Correct.
There's
Or 9 to 5, depending on which ones you're going, big to little or little to big. Yeah. What's the ratio of the areas?
25 to 81.
Yes. Very good. The areas are the square of the linear ratios. Linear ratios are 5 to 9, and the area ratios are 25 to 81, and the volume ratios would be 5 cubed over 9 cubed. So it depends on whether you're talking linear, area, or volume. Now, perimeter, a lot of people will assume that that's like area, but it's not. Perimeter is a linear measurement. It is one-dimensional. It's measured in feet. It's not measured in square feet or cubic feet. So whatever the measurement is tells you whether it's linear, an area, or a volume, whatever the units are. And you know perimeter is in feet. It's not square feet. All right, number 12. Two similar polygons, find the value of x and y. If I'm going to label the one on the left ABC, label the one on the right with prime.
A prime, B prime.
Where do I start?
So
this is B prime, because it tells us that angle is equal to that angle.
And then the one on the left of that would be C prime. And then A prime.
And the reason is because that angle is equal to that angle. So that makes that the A. Okay. And a lot of times when they give you these diagrams and they're rotated, it's difficult to tell which is the corresponding angles. We would have a hard time telling which is the corresponding angles here if they didn't give us this little hash mark. That tells us. Now, as far as figuring out the answer, what's x? Hold on. You look at this a second. What's b prime?
B prime is 133 degrees.
That tells you c prime. What's c prime?
C prime would be 180 minus
151, which is 29.
Okay, so x is equal to 29.
Well, we know 133 and this one's 18. So just by the fact that it's a triangle, we can figure out that that has to be 29. So those are the three angles, 29, 133, and 18, which makes that 18, and that's 29. So x is 29. Okay. Now, I want to know what y is. And what's kind of useful here is to know that x is an angle and y is a side. Well, they've told us that there's similar polygons. So how do I figure out? Give me an equation that gives the ratio equation where I can solve for y. Because it's a side, we know it's going to be in the form of
A ratio.
a ratio, yeah. Because in similar polygons, the angles are all equal, but the sides are not. However, the sides all have the same proportion. So what is the standard proportion between these two? In other words, what is the word I'm looking for is the similarity ratio. Similarity ratio. Have you heard of that?
No.
When you are dealing with two similar polygons, whatever the ratio between two corresponding sides are, is the similarity ratio. So what is it here? Either little to big or big to little. I don't care.
Let's do little to big.
Okay.
So it would be 1.25.
Hold on. Give me the ratio. Don't give me a decimal. You're going to go little to big. What's the ratio? The known ratio.
36.8
over
24.
No, over 46. In other words, you've got to make the ratio between the corresponding sides. Well, that 36.8 is opposite that same angle, the 133 degree angle, that the 46 is opposite. Now, I have to admit, you're not wrong. You can do these multiple ways, but I think for clarity's sake, you always want to do the corresponding sides. Okay? I'll say a little bit more about this after we finish the problem. But, okay, so what goes in the denominator on the right side? Y. Because we're going little to big. Y is the big side. Now, what's the little side?
16 or 20.
It's 24. No, hold on. Yeah. The reason it's 24 is because it's opposite. Y is opposite that angle, right? Well, that's that angle right there. Notice that this angle down here is opposite that hash mark. So opposite this hash mark is this angle. So this is the same as that. And opposite y is 24. Now we just have to solve that. You can go ahead and do that on your own. But let's talk about this again. Think about this for a moment. No, I can't think of what I was going to do. Let's just go on to 13. The problem in 12, 13, not so much 14 and 15, but 12 and 13 is they have rotated one of the similar polygons. And that makes it a little difficult to figure out why it's similar. I'm looking at 13. So this angle here is equal to what angle from the other one?
Angle.
Yeah, it's hard to even define because they don't have any letters.
Yeah.
But which angle is it? Is it top left, top right, bottom left, bottom right?
Top left.
Yeah, and the reason it is because that angle is opposite this single hash mark there. So I'm opposite that single hash mark.
Mm-hmm.
So I've got everything aligned properly. And then that, which is 4, is the same as this one here. So now we know how they're similar, and we're trying to solve for just x. Give me an equation.
X. X over 14 equals
X over
18.
Now I remember what I was going to do before. Yeah, that's fine. Equals what?
Equals 18 over 12.
Yeah, and then again, because x is in the numerator, you don't cross multiply. You just multiply both sides by 14.
Mm-hmm.
Okay, which I think gives you x equal 21.
Yes.
Okay. Now, in 14, they've made it really easy for us. They haven't rotated it. So, and again, x is a side and y is a side.
Mm-hmm.
So, tell me, first of all, what the similarity ratio is.
6 over 8, or 8 over 6.
Give it, okay. I don't care if you want to go little to big, that's fine. If you go big to little, it is 8 over 6. Okay? Mm-hmm. So, what's the equation that lets me solve for x? 8 over 6 equals what?
20 over x.
Yeah. And after you do a number of these, you'll get in the habit of putting your variable in the numerator, because that saves you one step. If the variable's in the numerator, you don't have to cross multiply and then divide. You just have to multiply. Nonetheless, this isn't that hard. You get 8x equals 120, x equals 15. And an equation for y?
Y would be 16. Y over 16.
Oh, this is where you got to make sure that you keep it big to little. Keep that consistent. This is big to little. Big, little.
Okay, 16 over y is...
That's correct. 8 over 6 equals 16 over y.
Mm-hmm.
That lets you solve for y. Yeah, the only mistake you can make on these problems is mixing up your big to little.
Yeah.
And this is why I always like to go one way only. I like to go big to little. I've found that big to little works a lot better than little to big, but every geometry teacher that I come across in Colorado teaches little over big. Don't know why, but they do. Okay, on 15. Again, they've made it really... No, they haven't made it so easy for us. Yes, they have.
Mm-hmm.
They're trying to confuse us with a single hash mark there and a double hash mark there, but those are corresponding sides. So, what are some equations? I don't care whether you go big to little or little to big, just be consistent.
Well, 6 to 4.
We're going big to little.
6 to 4 is equal to 16 over x.
Okay. That allows us to solve for x. What's another equation that lets us solve for y?
6 over 4 equals y over 10.
Yes. And notice that this is a little easier to solve. We'll only have one step to solving it. 60 divided by 4. So y is 15. Okay. Let's go to the next page. We got about 10 minutes here. Is that the middle one or the right one? Look at the middle one. No, we just did the middle one. Or right one, yeah. Okay.
Yeah.
Weird. Okay. Theorems for similar triangles. Name two similar triangles, also name the theorem or postulate that justifies it.
Okay.
When they say name two similar triangles, I guess they're talking about just problem number 1?
Yes.
Okay.
There's triangle ABC and EFD. If you flip it.
Yeah. How do you know those are similar?
Right angle.
Well, how do you know this is a right angle?
You don't. It's because of the sides.
It's because it's side, side, side. In other words, if we were to reduce this, this would be a 3, 4, 5 right triangle. And if we reduce this one over here by dividing everything by 6, we have a 3, 4, 5 right triangle. And so the postulate is what?
Side, side, side. Whoa.
I guess, yeah. I actually am not familiar with the postulates that prove similarity. But you're right. If the ratio of the 3 sides are all the same, then it's similar, I would say also by side, 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 although these are not 3 similar sides. They're all different lengths. In other words, this is 9, 12, 15. This is 18, 24, 30. I guess the postulate is the following. If you have a triangle that is a 3, 4, 5 triangle, it is by definition a right triangle. You cannot have a 3, 4, 5 triangle without it being a right triangle, believe it or not. In other words, it works both ways. The Pythagorean theorem works both ways. If you have a right triangle, the sum of the squares of the sides equals the hypotenuse squared. And the corollary to that is if you have a triangle where the sum of the square of the 2 short sides is equal to the square of the long side, then you have a right triangle also. And the fact that that is a right angle and that is a right angle, and the fact that they are both 3, 4, 5 right triangles mean that has to be the same and that has to be the same as those 2 angles A and B. And so really what you actually have is Angle, angle, angle. Actually, angle, angle is the only postulate I've ever heard of for proving similarity. I guess side, side, side also does it. But you'd have to prove that the ratio of each corresponding side is the same in all cases here. What's the similarity ratio between these two triangles?
In number 1?
Yeah.
1 to 2.
1 to 2, or 2 to 1 if you're going big to little. Okay. Let's look at number 2.
You got triangle ASC and ATR that are similar.
Why?
Because of the sides, and then the 45-degree angle, and then I guess another side. So I think it's side, angle, side.
Yeah, I think you're right.
Because if it works for congruency, then it would have to work for...
Well, the key is for congruency, the sides have to be equal. But when you're proving similarity, the ratios have to be equal. So it's still side 1 over side 2, angle side 3 over side 4. So that ratio of those two sides, which in this case is 8 to 12, is the same as 6 to 9. So we have 8 to 12 over 6 to 9. That's both 2/3, and there's an angle in between. So I guess geometrically that is considered proof. Although you're one of the few people I've ever had a question regarding this, to name the theorem that proves similarity. Yeah, nobody else ever tells me or asks me about that.
Yeah.
Okay, and 3. What are the similar and why?
We got triangle CAB,
Okay.
CDE.
So those are similar. Why?
Because of the side angle side again, I guess.
Yeah, and it's side ratio. In other words, this side here, it's 3 is to 9. The angle is angle C, that's the same. And the other one is 5 is to 15. Or you could even say 3 is to 6 and 5 is to 10. It doesn't really matter. You get the same answer. So you can either go that relative to that, or you can go that relative to the whole line. Actually, when you're considering similar triangles, you really should go that relative to the whole line, right? Because what you're really proving is that this triangle is similar to this triangle. So I really need to do that little side relative to the whole side, which is 9. Although you can take a shortcut and do 3 is to 6 as 5 is to 10. And that was kind of what I was thinking about before. Now let me give you a little different aspect here. Just, you might not be aware of this, and this is actually pretty worth being aware of. When you have similar triangles, which we do here, there's a bunch of ratios that apply. It's not just ratios. In other words, we know 3 is to 6 is equal to 5 is to 10, right? In other words, the ratio of corresponding sides are the same. But there's other ratios that are also correct. I'll let you go here in a second. But I can also say that 3 is to 5 as 6 is to 10. In other words, it's not just the ratio of corresponding sides, it's also one side is to another as one side is to another. Or 3 is to 4 as 6 is to 8. So it's not only the corresponding sides between the triangles, it's also the ratio of the sides of one triangle is the same as the ratio of the sides of another triangle. So there's multiple ratios that can be made into equations. And that's worth knowing because sometimes it's just easier to do it a certain way. If I put an x there, then I probably want to say x is to 8 as 3 is to 4, right? Now I can solve it really quick. X has to be equal to 6. Whereas if I were to say 3 is to x as 4 is to 8, makes it a little harder to solve. Now my x is in the denominator, and I got to cross multiply and divide. So just wanted to point that out.
Okay.
Okay. Joseph, you have a good evening, and I'll talk to you next time.
You too. Thank you.